My name is Scott Davidoff, and I manage human-centered design over at the Jet Propulsion Lab in Mission Operations. And I am going to kick off this session by giving a talk, and then I'm going to be introducing the subsequent guests. So allow me to introduce myself. I've been working at the intersection of interactive data visualization and virtual reality since I came to the Jet Propulsion Lab 6 years ago. And what I would like to talk about is to show some of the work that we've been doing in an ongoing basis in virtual reality and augmented reality, and then put right next to it the work that we're doing in interactive data visualization, and then talk about how we start to break down the walls between these disciplines and find opportunities for really thinking through what these technologies can do together. So I think the first work that I'd like to show is something that Parker, who's going to be speaking next, is really going to go into in a bit of detail. But this is essentially a scene that we've reconstructed from basically data that characterize the topology of Mars. And this application is something that we've been able to find geologists can actually put the HoloLens on and interpret the environment in a way that is radically different than the way that they've been interpreting it using flat imagery or cylindrical panoramas. So Parker will talk a little bit more about that. But what makes this interesting is, I think, consistent with many of the things that the other speakers here have been describing today, in that we're representing, with really verisimilitude, an inherently 3D environment. So this is not an abstract data problem, right? This is space that we're representing spatially. So in many ways, it's less surprising, but what's exciting is to see how scientists, when they are inside of it, can perceive the environment in the first person and gauge distances relative to their bodies in a way that is very different than trying to estimate distance given basically a 2D image. So let me show you a few more examples and then talk about the interactive data visualization work. So this is an example of basically controlling a robot avatar. So here, what we're trying to do is operate a very high degree of freedom robot arm. And the hypothesis behind this work was that by effectively allowing the author, right, the controller, to command the robot as though the arm were their own, that this would create tremendous affordances and allow the operator to actually much more quickly be able to command what is effectively very difficult to program. And you can see here the operator looking at this virtual space. And so there's a couple of very high-level findings. The first is that it takes a very complicated act, like programming a high degree of freedom robot arm, and makes it into a much faster set of operations. But I actually think it's important to go back to one of the things that Wolfgang was talking about earlier, which is what you have also is a tremendous number of degrees of freedom that you now have to control with precision. And it turns out that the hand is actually not incredibly precise when it's at different degrees away from the body. And so one of the things that we found is that it actually makes things very fast, but at the same time, the imprecision in your hand motion, when interpreted by the cameras, actually added a different kind of difficulty than existed in programming the arm. And so, interestingly, the hypothesis was 6 degrees of freedom would lead to more control. And in some ways, 6 degrees of freedom led to faster control, but 6 degrees of freedom led to less fine detail precision. And I think that's a very important takeaway as we try to hypothesize how might we extend immersive environments to provide support for scientists and engineers trying to solve other complex problems. One more example from virtual reality. this is an application that was also developed in collaboration with my group at the Jet Propulsion Lab. What you're seeing here is a capture of a device that allows a team of mechanical engineers to stand around a virtual model. So this is effectively a kind of CAD visualizer. So what's interesting about this? Again, you have a very inherently 3D task that teams can now look at together. So one of the things that were interesting and surprising about this were that one of the things that teams have really never been able to do very early in the design process was actually stand around a virtual model together. And what you see here is this is not one person, which is actually the interaction metaphor of many CAD applications, right? It's one person at one screen. But it takes a village to build a spacecraft. And I think what you're seeing here is the team being able to stand around and judge relative size in a way that they've never been able to before. And so I think one of the big takeaways is that virtual reality, or augmented reality in this case, really gave people the ability to communicate around technical concepts and accomplish a technical agenda in a way that was considerably difficult before. I think this is very consistent with George and Chiro's early work in the virtual observatory, where you had scientists getting to meet and you created this imagined virtual space that they could actually collaborate in. So what are the things that these ideas have in common? Well, first of all, I think what we were tending to do was show that they could visualize extreme environments that are otherwise quite difficult for us to actually be able to visit. So Mars is a great example, but other things are undersea, volcanic vents. Basically, when many of the objects that our physical scientists tend to study. So I feel like it's a good fit in that way. And whenever you need to represent some main elements of this world that have a consistent verisimilitude. So in other words, Mars has a spatial orientation and you want to talk about a spatial orientation. And it created this ability to collaborate in ways, but also a shared reference frame. So what are the things that made it difficult? Well, you have this 6 degree of freedom selection, of course, which has this imprecision. Then you have occlusion, right? So that data points that a small data point could easily be blocked by a large one. And then similarly, perspective, that when an object is far, it's hard to tell how far, if it's large and close and far away, or small and closer. Those are things that are difficult. Now, something that Doug pointed out was this idea that I would describe comes from the visualization research as like this focus plus context, or the idea of different kind of workspaces. So it's, I think, very interesting to think about the challenges of what this means by being able to see data at different scales at the same time. And this is one of the essential challenges to be able to do effective analytics work in a very detailed way. So for example, if you're looking at earth science data, I think there are many examples of creating a virtual reality globe, and that's one level of vision, but to actually be able to do analysis operations on a model requires that you also be able to look at different kinds of parameterization. So how do we resolve this? And then one other thing is this idea of, what I want to talk about, the analytics ecosystem. This is one other thing that I feel like I've heard a couple of different perspectives on, I think is really interesting. So to some extent, certainly virtual reality creates a strong barrier between being in it and not being in it. And a lot of these scientific analyses happen with other people or in offices, and there's a pretty finite limit to the amount of analytic horsepower that we're able to put into any one of these applications. So when we create these special applications that allow you to, for example, to view data in a particular kind of way, that's a very small piece of the actual workflow that a scientist needs to do. So if a scientist wants to see the model, and then they need to adjust the parameters, and then often they'll want to go in and program, and then they'll want to see the changes of their model, and they'll want to go back. So there's an analytic loop that is actually supported differently by an ecosystem of tools. And so very often, these tools that we create will be very special purpose. And this is one of the just inherent barriers to actually allowing people to be able to accomplish meaningful work. And I think there are very good reasons to try to say, let's not make the analytic, tool to rule them all. But there's also good reasons to realize that every barrier we create where someone's going to take off the headset and move into another environment is going to create an opportunity for them to not use the tool. So it's a very interesting challenge that I think we have to think about how to face. Let me show you very quickly some examples of some analytics applications, and then start to think about how we might merge analytics and visualization. So here is a project that I worked on with the JPL rover planner team and some colleagues, including Santiago, who's here in the audience at Caltech. So this idea was to create a tool that would allow rover drivers to understand how to pilot a rover on another planet. And there are these essential physical hazards to piloting a rover safely, and a very high cost of driving it off a cliff, for example. And so what we decided to do was find a way to, designing the path for the rover is also a fairly expensive operation. And it's the kind of thing that is done by programming. And so what we hypothesized is by creating a tool that allowed the rover drivers to sketch, effectively come up with lightweight ways to evaluate the safety of different paths. And so we came up with this is just something to show how we're including some of the variables that they evaluate, like pitch and roll. And so we came up with a number of different encodings. But let me jump to the tool. So here's an example of the tool and some of the very beginnings. The first thing we wanted to do was give the scientists, the rover planners, the ability to draw different paths. And so they can leave waypoints and effectively create different paths. And what the rover planner can then do is interactively look at where the spacecraft would be and understand these quantitative measures of the path. So for example, here, the rover driver is moving the end and seeing how that changes the slope of the path that the rover driver would be doing. So what you can see here is we've given someone this interactive thinking tool that allowed them to try different alternatives. And in this visualization, what you've seen is on the rover path, we are plotting the pitch using these histogram bars and the slope using the color. And so what the rover driver does is actually drag the head of the path. Here they're going to delete the path, and maybe we can start over so you can just see that again. So what they'll do is drag the path and see how the variables change dynamically. So this is a very interesting interactive tool because it allows the rover driver to make very subtle adjustments that they would have to do just entirely in programming. So I am going to jump to the kind of questions that I would like to ask here, just because I'd like to be sensitive to our time. So I wanted to ask this question about visualization and virtual reality. I mean, is it, in fact, an exciting fusion, or is this a kind of awkward couple? And I think it actually has the potential to do many of these things. So the hypothesis that I would like us to think about is what are the things that we might do that could take advantage of the benefits of both and be wary of the limitations that we have learned through doing work in each of these areas. So I think one of the questions that we've seen is this idea about whether we should have expressly spatial environments or entirely abstract data. And I'm actually suggesting a merger of the two. I'm suggesting that we use the display to focus on a spatial task, and that we overlay analyses that are often done in 2 or 3D on top of that spatial component. And this would allow us to get the advantages that we have in being able to see something in virtual reality or augmented reality, and also have these analytic capabilities. And I'll jump to this point down here. And I feel like, in many ways, by having these real objects that have a mixture of real and what I'll call magical properties, so that we're going to get this force multiplier effect. So superpowers is effectively how I'm thinking about them. So I might be able to see a spacecraft, and that's a real object, but I can't invoke a thermal model of the properties of the thermal distribution of the spacecraft. And that would feel, I feel, like a real kind of analysis in the real world that they're unable to do currently. And so if we would think about the kinds of things that this analysis group has been able to do, starting with CAD is really an effective first application. But what I think we really can do is move earlier and earlier in the actual process of engineering so that all the different effective models that the design team would like to be able to use to support their design. They want to know, if I add this part, what is the mass difference now? So, right, just a quantitative variable. What is the effect on the lifetime of the spacecraft? What is the effect on the thermal properties of the spacecraft? So these are models from different domains that I think if we could figure out how to fuse, we would really, I think, be able to get the space-orienting capabilities of VR and the analytic superpowers that have come from visual analytics. So just so that we're mindful of the time, I'm going to cut myself off and say I really look forward to using these ideas as prompts to ask questions of the people in the audience about the kinds of technical challenges that they are looking to solve. And I believe that we can extend these ideas into how we model gravitational waves from black holes. And that it's inherently a physical and an analytic property. How we model glacier land-sea ice interaction. Right? It's a physical and analytic property. There are models, and we want to understand and measure where model residuals are imperfect, and use the physical space to allow us to gain insights that 2D analytics make harder for us to extrapolate, effectively taking advantage of our spatial perception and the analytic powers of visual analytics. Thanks very much, everybody. So do we have a moment for questions, George? Or? Okay. Yes, thank you.
Nice presentation, Scott. Just one question regarding the superpowers. Okay. How do you think, or how do you see programming in augmented reality? Because one of the problems I think that in hard science that we have is actually that we interact with software usually.
Yes.
So how do you see this machine learning assisted programming or something like that?
Okay. So there's, I think, a few questions that are kind of embedded in that one question. And I actually think Parker can really talk to some of these ideas earlier in his talk. But for example, one of the early instances of the on-site tool that Parker is going to show actually included a Martian landscape and cut out the display. So if you were looking at your display, you could effectively use it as you normally would. And so this would allow the scientist to both be able to get first-person experience, and then if they wanted to change an aspect in the model, actually be able to use a desktop a continuous version of the application. And so they could actually have a mouse in the environment, click on a place in the environment, save that point to their desktop, and then run an analysis to maybe see the source imagery, for example. So now, just maybe what we can do is take the question about machine learning and a little bit more sophisticated interaction offline. But anyway, thank you very much.